Have you ever looked up at the night sky and wondered if someone or something out there is looking back? Picture a message sent billions of years ago, racing through the void at the speed of light, carrying secrets from the farthest corners of the cosmos. These are the forgotten signals, the lost whispers of the universe that have traveled farther and longer than anything humans have ever created. They're not just random noise or cosmic static. They are echoes of events so ancient, so unimaginably distant, that by the time they reach us, the stars that birthed them may have already burned out. And yet, here they are, faint but persistent, waiting for us to listen. What if I told you that some of these signals defy everything we know about physics? That they arrive in bursts of energy so powerful, they outshine entire galaxies for just a fraction of a second, or that others repeat in patterns so precise, they seem almost intentional. These aren't just scientific curiosities, they're cosmic mysteries that have left astronomers scratching their heads for decades. Some could be the remnants of collapsing stars or the death throes of black holes. Others, well, there's a reason they've sparked theories about civilizations far older and more advanced than our own. This is the story of those signals, the ones that slipped through the cracks of time, the ones we almost missed, and the ones that still haunt our telescopes today. It's a journey that will take us from the silent depths of space to the cutting-edge labs where scientists strain to decode the universe's oldest messages. And along the way, we'll ask the biggest question of all. What if these whispers aren't just echoes of the past, but clues to our future? Strap in, because we're about to follow these signals to the very edge of what we know, and maybe, just maybe, beyond. That summer night in 1977, the universe sent us a message, or at least, that's what it felt like. The Big Ear radio telescope in Ohio, a humble array of metal and wires scanning the skies for whispers from the cosmos, suddenly caught something extraordinary. For 72 seconds, a signal blazed across its receivers so intense that it dwarfed the usual background noise of space. When astronomer Jerry Amon reviewed the data printout days later, he was stunned. The numbers told a story he couldn't ignore. In red pen, he circled the sequence and scrawled a single word in the margin. Wow, and just like that, a mystery was born. What made this signal so special? For starters, it wasn't some faint blip lost in the static. It was loud, so loud that if it were a voice shouting across space, it would have been screaming directly into our ears. It also had a frequency close to 1420 megahertz, a quiet channel where human-made interference is minimal and where scientists had theorized an advanced civilization might broadcast. But here's the strangest part. After those 72 seconds, it vanished. No follow-up, no repeats, just silence. For decades, astronomers have chased explanations. Could it have been a comet, a passing satellite, a glitch in the telescope itself? Each theory has holes. Comets don't emit such strong, narrow-band signals. Satellites weren't known to operate at that frequency back then, and glitches don't usually leave such a pristine, one-of-a-kind fingerprint. The more we've searched for answers, the more the wow. Signal stands alone, a cosmic flare that appeared, dazzled us, and then slipped back into the dark. But what if it wasn't just space noise? What if, somewhere near the constellation Sagittarius, something, or someone briefly turned a transmitter in our direction? The idea isn't as far-fetched as it sounds. In the vast ocean of time, 72 seconds is nothing. A civilization could have sent that signal millions of years ago, only for us to catch it by pure chance, like finding a single bottle washed ashore from an ancient shipwreck. And if that's true, what else might still be drifting toward us, unseen, unheard, waiting for the right moment to be discovered? The wow signal is more than a scientific curiosity. It's a reminder that the universe is full of voices we've only just begun to hear. Fast radio bursts are like the universe playing a game of cosmic Morse code, blinking into existence for just a fraction of a second, then disappearing before we can fully grasp what we've witnessed. First detected in 2007 by a team sifting through old telescope data, these bursts pack more energy in that fleeting moment than our sun emits in 80 years. And they're not coming from next door. Some originate billions of light years away, from galaxies so distant their light has traveled across eons just to reach us. What makes FRBs so baffling isn't just their power or distance, it's their unpredictability. Most appear once and never repeat, like a door slamming shut in the dark. But a handful have been caught sending follow-up signals, pulsing at irregular intervals that defy easy explanation. Take FRB 121102, a repeater located 3 billion light-years away. It follows no discernible schedule, sometimes firing off multiple bursts in an hour before going silent for months. It's as if the universe is teasing us, offering glimpses of a pattern just beyond our understanding. Theories abound, each more fascinating than the last. Could these bursts be the aftermath of neutron stars' ultra-dense stellar corpses colliding or collapsing into black holes? Maybe, but then there's the sheer precision of some signals, their frequencies so clean they almost resemble engineered transmissions. That's led some to speculate about advanced civilizations harnessing unimaginable energy to power interstellar beacons. Even if the odds are slim, the idea forces us to confront a humbling truth. In a cosmos this vast, we're only beginning to learn the rules. Recent discoveries have only deepened the intrigue. In 2020, astronomers detected an FRB from within our own Milky Way, finally linking one of these bursts to a known celestial object, a highly magnetic neutron star called a magnetar. But here's the twist: while this burst shared traits with its distant cousins, it was far weaker. So if magnetars explain some FRBs, what's cranking the volume to 11 in those faraway galaxies? The answer might lie in phenomena we've yet to imagine, let alone observe. Every new detection feels like finding a single puzzle piece from a box scattered across the cosmos. Are these bursts natural cosmic fireworks or something more deliberate? For now, they remain tantalizing enigmas, brief flashes in the void that challenge our assumptions and ignite our curiosity. One thing's certain: each pulse carries secrets from the depths of space and time, and decoding them might rewrite what we know about the universe itself. In 1967, a young graduate student named Jocelyn Bell was reviewing data from a radio telescope in Cambridge when she noticed something peculiar: a series of pulses so regular they could have been ticking off the seconds of a cosmic clock. These weren't the usual chaotic blips of interstellar noise. They arrived every 1.337 seconds with unerring precision, like a heartbeat from the depths of space. The signal was so unnervingly consistent that Bell and her advisor, Anthony Hewish, jokingly labeled it LGM-1, short for Little Green Men. For a brief, thrilling moment, the idea that they might have stumbled upon a beacon from an alien civilization didn't seem entirely far-fetched. What Bell had actually discovered was far stranger than science fiction. The first known pulsar, a rapidly spinning neutron star. These stellar corpses, no larger than a city but denser than the sun, emit beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like a lighthouse, appearing as rhythmic pulses when they intersect with Earth. The discovery revolutionized astrophysics, proving that nature could produce signals so precise they rivaled human-made technology. But it also raised a humbling question. If something as mundane as a dead star could mimic an alien transmission so convincingly, how many other intelligent signals might we be misreading? The LGM-1 story isn't just about scientific triumph, it's a cautionary tale. Even today, as we scour the cosmos for signs of life, we're haunted by the possibility that the universe is playing tricks on us. Take the infamous Tabby star, whose erratic dimming sparked wild theories about alien megastructures, only for dust clouds to emerge as the likely culprit. Or the recent LGM-1 signal from Proxima Centauri, which initially seemed to originate from our nearest stellar neighbor, but was later traced to earthly interference. Each time, the line between natural wonder and artificial design blurs a little more. Pulsars themselves continue to defy expectations. Some, like the Black Widow pulsar, devour their companion stars, while others, like the millisecond pulsars, spin hundreds of times per second faster than a kitchen blender. Yet despite their variety, they all share one eerie trait. Their pulses are so reliable, they're used as cosmic timekeepers, helping astronomers navigate the galaxy. It's a reminder that the universe doesn't need intelligence to create order. Sometimes, chaos collapses into patterns all on its own. So the next time we detect a signal that seems too perfect, too deliberate, we do well to remember Jocelyn Bell's pulsar. Not as a dismissal of the search for extraterrestrial life, but as a lesson in humility. The cosmos is vast, ancient, and endlessly inventive. Before we jump to conclusions about who or what might be sending messages, we have to reckon with a simpler yet profound truth. Nature often wears the mask of intelligence, and the most alien thing out there might just be the universe itself. Back in 1961, astronomer Frank Drake scribbled an equation on a chalkboard that would change how we think about our place in the cosmos. At first glance, it looks deceptively simple, a string of variables multiplied together, like a cosmic recipe for intelligent life. But this wasn't just math. It was a doorway to one of humanity's oldest questions: are we alone? The Drake equation doesn't give us a definitive answer, but it does something even more powerful. It turns speculation into science, giving us a framework to quantify the unquantifiable. Let's break it down. The equation starts with the rate of star formation in our galaxy. How many new suns are born each year? Then it asks what fraction of those stars have planets. How many of those planets could support life? Of those, how many actually develop life and intelligence and technology? And finally, how long might those civilizations last before vanishing? Each variable is a cliffhanger, a leap of faith backed by evolving science. When Drake first proposed it, we didn't even know if other stars had planets. Today, thanks to telescopes like Kepler, we've confirmed thousands, and yet the biggest questions remain. Here's where things get humbling. Plug in the most optimistic numbers, and the equation suggests the Milky Way could be buzzing with civilizations. But use conservative estimates, and the result drops to near zero. That staggering range isn't a flaw, it's the point. The equation mirrors our ignorance, highlighting just how much we still don't know. Take the last variable, the average lifespan of a technological civilization. Are we talking centuries, millennia, or, given humanity's own precarious trajectory, something far shorter? Suddenly, the math becomes a mirror, forcing us to confront our own fragility. So why, in a galaxy that could be teeming with potential neighbors, have we heard nothing? This is the Fermi Paradox in action, the eerie silence that contradicts the equation's possibilities. Maybe civilizations are too far apart in time or space, their signals fading before they reach us. Maybe they're too advanced, communicating in ways we can't yet detect. Or maybe, tragically, intelligent life tends to self-destruct before it can colonize the stars. Each theory is a story we tell ourselves to explain the quiet. Yet the Drake equation endures, not because it solves the mystery, but because it keeps us searching. Every discovery, every Earth-like planet, every extremophile organism thriving in hostile environments tweaks the variables, nudging the odds. It reminds us that science isn't just about answers. Sometimes it's about asking the right questions, even if the universe isn't quite ready to reply. So the next time you look up at the stars, remember that equation isn't just a calculation. It's a promise that the cosmos still has stories left to tell. For over 6 decades, scientists have trained radio telescopes on the stars, listening for a signal that would shake humanity to its core, a whisper from another world. This is the mission of SETI, the search for extraterrestrial intelligence, a quest that turns our most powerful receivers toward the cosmos, scanning frequencies where the universe falls unnaturally silent. The logic is simple. If civilizations exist out there, they might leave footprints in the electromagnetic spectrum, whether intentionally or as cosmic side effects of their technology. But after all these years of listening, the silence has been deafening. Not a single confirmed transmission, not one unmistakable hello. So what gives? The challenge isn't just distance, it's time. Imagine 2 people standing on opposite shores of an ocean, each holding a flashlight. If they flicker their lights at random, the odds of catching each other's signal are vanishingly small. Now scale that up to galactic proportions. A civilization could have broadcasted a message thousands of years ago, aimed in our direction, and we'd miss it simply because we weren't listening yet, or worse, their signal hasn't even reached us. And then there's the needle in a haystack problem. The radio spectrum is vast, and tuning into the right frequency at the right moment is like winning a cosmic lottery. But here's where things get exciting. Modern SETI isn't just relying on patience and luck anymore. Artificial intelligence is changing the game, sifting through terabytes of telescope data at speeds no human team could match. Machine learning algorithms now scan for anomalies, patterns that don't fit the usual cosmic static, signals that flicker or repeat in ways nature shouldn't. In 2020, one such AI flagged a candidate from Proxima Centauri, a tantalizing blip that, while likely interference, showed the potential of this approach. The truth might already be hiding in decades of archived data, waiting for the right algorithm to uncover it. Then there's the question of what we're even listening for. Early SETI focused on narrowband signals, precise, unnatural tones that scream artificial. But what if advanced civilizations communicate in ways we haven't imagined? Perhaps they've moved beyond radio, using neutrino beams or quantum entanglement, technologies still in their infancy for us. Or maybe they're deliberately quiet, hiding from something or someone out there. The unsettling dark forest hypothesis suggests that silence might be a survival strategy in a universe where first contact could be fatal. Despite the cosmic quiet, SETI presses on, buoyed by discoveries that keep the dream alive. Every new exoplanet in a habitable zone, every extremophile organism thriving in Earth's harshest environments, expands the possibilities. Projects like Breakthrough Listen Now scan millions of stars, while initiatives like SETI at home harness the spare processing power of home computers worldwide. It's a collective effort, a testament to humanity's refusal to accept solitude. Because if we stop listening, we'll never know, and that silence, more than any signal, might be the most haunting answer of all. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, a visitor from another star. They named it Amuamua, Hawaiian for scout, and from the moment it was detected, this strange, tumbling object defied expectations. Unlike any comet or asteroid we'd seen before, it was shaped like a cigar 10 times longer than it was wide, and it wasn't just drifting. It was accelerating as if pushed by some unseen force. The more data scientists collected, the more perplexing it became. No visible tail of gas, no dusty coma. Just a silent, speeding enigma, already racing out of our solar system by the time we noticed it. Theories flew fast. Maybe it was a fragment of a shattered planet, ejected from some distant star system. Maybe a rare hydrogen iceberg, sublimating in sunlight and leaving no trace. But then came the observation that lit the fuse of speculation. Its trajectory didn't match the gentle nudge of outgassing, the usual explanation for a comet's acceleration. The numbers were off, just enough to make even seasoned researchers pause. That's when Harvard astrophysicist Avi Loeb floated a provocative idea. Could Amuamua be artificial? A light sail, perhaps propelled by starlight technology humans are only beginning to explore. The scientific community bristled, but the question lingered. After all, if we're willing to scan the skies for alien radio signals, why not consider the possibility that artifacts might sail right past us? What makes Amuamua so tantalizing isn't just its strangeness, it's the timing. Its discovery came mere years before we spotted our second interstellar visitor, the far more comet-like Borisov. That contrast raises a chilling possibility. If Borisov is the normal interstellar object, what does that make Amuamua? A statistical fluke or a glimpse of something far more extraordinary? The truth is, we'll likely never know for sure. By the time telescopes could turn toward it in earnest, the object was already too distant, too faint. All we have are those fleeting observations, a handful of data points that refuse to fit neatly into any box. And that's the real lesson here. Amuamua isn't just a mystery, it's a wake-up call. If interstellar visitors slip through our cosmic neighborhood so frequently, scientists estimate there could be thousands inside our solar system at any given time. How many have we missed? How many more will we overlook unless we're watching closely? Projects like the Vera Rubin Observatory, set to scan the entire visible sky every few nights, promise to catch the next one sooner. But the deeper question remains, in a universe as vast and ancient as ours, how do we distinguish the natural from the engineered? The answer might require more than better telescopes. It might demand a whole new way of seeing. So while Amuamua slips forever beyond our reach, its legacy endures, not as proof of aliens, but as a reminder that the cosmos still holds surprises that defy our textbooks. The next time an interstellar stranger pays a visit, we'll be ready. And who knows, maybe it won't just be a rock. Maybe it'll be a message or a messenger waiting patiently for us to recognize it for what it truly is. The night sky holds a secret, one that should be impossible to miss. With hundreds of billions of stars in our galaxy alone, and many of those stars hosting planets in the so-called Goldilocks zone where life could thrive, the math suggests the cosmos should be buzzing with activity. And yet, when we listen, when we search, all we hear is silence. This is the Fermi Paradox in all its unsettling glory. If the universe is so vast and ancient, where is everybody? One explanation cuts deeper than the rest: the Great Filter. Imagine a series of hurdles so immense that almost no civilization can clear them all. Maybe life itself is vanishingly rare, emerging only under perfect conditions we don't yet understand. Or perhaps the filter lies ahead of us, some catastrophic event, nuclear war, runaway AI, ecological collapse that wipes out intelligent species before they can spread beyond their home worlds. The chilling thought, if the filter is in our future, humanity might already be on borrowed time. But let's not jump to doomsday scenarios just yet. There are gentler possibilities. Advanced civilizations might communicate in ways we can't yet perceive, using technologies far beyond our grasp. Think about how an ant colony perceives a smartphone, not as a tool but as a meaningless rock. If aliens exist, their messages could be all around us, encoded in neutrinos or dark matter, waiting for us to evolve enough to notice. Then there's the zoo hypothesis, the idea that Earth is purposely being left undisturbed, like some cosmic wildlife preserve. Maybe we're being observed from a distance, intentionally isolated until we reach a certain level of maturity. It's a comforting thought until you consider who or what might be playing the role of zookeeper. Of course, the simplest answer is often the most humbling. Space is big, unimaginably big. Even if civilizations are common, the distances and timescales involved might make contact impossible. A civilization could rise and fall in a neighboring star system, and we'd never know. Their signals might reach us millions of years after they're gone, or ours might arrive long after their species has faded into dust. The Fermi Paradox isn't just about aliens, it's a mirror. Every theory reflects our hopes, our fears, and our growing awareness of how little we truly understand. Whether the answer is tragic, wondrous, or something beyond our current imagination, one thing is certain: the silence isn't empty. It's full of questions, and those questions might just be the most important ones we'll ever ask. Imagine a whisper from the dawn of time, a faint, crackling hum that fills every inch of the cosmos. This is the cosmic microwave background radiation, the afterglow of the Big Bang itself. It's the oldest light in existence, stretched and cooled over 13.8 billion years into a ghostly microwave signal that bathes the universe. But what if this ancient echo isn't just a relic? What if, buried in its subtle fluctuations, lies something more deliberate? The CMB, as scientists call it, is like a baby picture of the universe. Its tiny temperature variations, warmer and cooler patches no larger than 100,000th of a degree, reveal the seeds of everything we see today: galaxies, clusters, the vast cosmic web. For decades, we've studied these patterns to understand the origins of space and time. But here's where things get wild. Some theorists propose that an ultra-advanced civilization could have manipulated this radiation, encoding information within its very fabric. Think about it. If you wanted to send a message that would last for eternity, reach every corner of the cosmos, and survive the death of stars, where better to hide it than in the universe's oldest broadcast? The idea isn't as far-fetched as it sounds. In 2005, physicist Stephen HSU suggested that a civilization with godlike technology could alter the CMB's polarization, the orientation of its light waves, to create a binary code visible to anyone who knew where to look. The message wouldn't need to be complex. Even a simple sequence of prime numbers or mathematical constants would scream artificial against the randomness of nature. And because the CMB is everywhere, the signal would be universal, a cosmic hello etched into the sky itself. Of course, mainstream science remains skeptical. The CMB's patterns align perfectly with our models of the early universe's quantum fluctuations. But that's the thing about breakthroughs, they often lurk at the edges of the impossible. Consider the cold spot, a peculiar region in the CMB that's significantly cooler than its surroundings. Some have speculated it could be evidence of a parallel universe brushing against ours. Others argue it's just a statistical fluke. But what if it's neither? What if it's a signature, a fingerprint left by something, or someone playing with the building blocks of reality? The beauty of this theory lies in its audacity. It forces us to rethink not just how aliens might communicate, but when. A message in the CMB would have been encoded billions of years ago, perhaps by a civilization that rose and fell before Earth even formed. Their words would be older than stars, carried on light that outlasts time. And if we ever found it, the implications would shatter our understanding of intelligence's place in the cosmos. So while we map the CMB's whispers for clues about dark energy or inflation, let's keep one ear open for the unexpected. The universe's oldest signal might still have secrets to tell, not just about where we came from, but about who else might be listening. After all, if you wanted to leave a note for eternity, wouldn't you write it in the sky? In 1974, humanity took its first deliberate step into the cosmic conversation. The Arecibo Observatory, a massive radio telescope nestled in the jungles of Puerto Rico, turned its dish toward the heavens and unleashed a carefully crafted message into the void. Aimed at the star cluster M13, 25,000 light-years away, this 3-minute broadcast wasn't just static or noise. It was a meticulously designed cipher, a digital handshake from Earth to the stars. At first glance, the Arecibo message looks like a simple grid of ones and zeros, but those binary digits form a pictogram, a visual snapshot of who we are. It starts with the numbers 1 through 10, written in binary, a universal language any advanced civilization should recognize. Then come the building blocks of life itself: hydrogen, carbon, nitrogen, oxygen, and phosphorus, the chemical ingredients of human DNA. The message sketches our double helix structure, followed by a stick figure human, a diagram of our solar system with Earth highlighted, and finally, an illustration of the Arecibo telescope that sent it. It's humanity's resume compressed into 1,679 bits. But here's the catch: that star cluster it was aimed at. By the time the message arrives, M13 will have drifted out of position. The odds of it reaching an inhabited world are astronomically low. That was never really the point. The Arecibo message wasn't about practical contact. It was a symbolic act, a declaration that we're ready to be part of something bigger. A cosmic message in a bottle, flung into the ocean of space with no expectation of reply. Yet the real brilliance of the message lies in what it assumes about its recipients. To decode it, an alien civilization would need to recognize binary math, understand the atomic structures we've included, and interpret two-dimensional images from a linear data stream. That's a lot of shared knowledge to take for granted. It's like trying to explain a sunset using only emojis possible, but fraught with room for misunderstanding. What if they read our DNA diagram as instructions rather than description, or mistake the telescope illustration for an object of worship? The message is a Rorschach test, revealing as much about our hopes as it does about our limitations. And then there's the timeline. 25,000 years is longer than human civilization has existed. By the time the signal reaches its target, if anyone is there to hear it, we might be long gone. Our species evolved beyond recognition or vanished entirely. The Arecibo message is less a phone call to the stars and more a time capsule, a whisper from a younger, bolder version of ourselves. But perhaps that's the most profound lesson here. The act of sending the message changed us. It forced scientists to think deeply about how to represent humanity in a way that transcends language or culture. It reminded us that communication isn't just about speaking, it's about being understood. And most of all, it proved we're no longer content to just listen. We want the cosmos to know we're here, even if the only reply is the echo of our own ambition. So while we wait for signals that may never come, the Arecibo message continues its silent journey. It's out there right now, racing through the dark at the speed of light, a tiny spark in the infinite night, carrying the essence of who we were, who we are, and who we might yet become. Imagine a forest at night, a place where every rustle could be a predator, every flicker of movement a threat. Now picture that forest spanning the entire cosmos, where civilizations like wary animals hide in the shadows, terrified of drawing attention. This is the dark forest theory, a spine-chilling answer to the Fermi Paradox that suggests the universe isn't just silent, it's silent by design. The logic is brutal. Any civilization that announces its presence risks annihilation by something older, smarter, or more ruthless. So they stay quiet, they hide, and if they're watching us right now, they're doing it from the darkest corners of space, careful not to make a sound. The theory borrows its name from Liu Cixin's sci-fi masterpiece, The Three-Body Problem, but its roots dig deep into real-world game theory. Think of it like this. In a universe where resources are finite and trust is non-existent, the safest strategy isn't to reach out, it's to shoot first. A civilization might assume others operate the same way, preemptively striking potential rivals before they become threats. The result, a cosmic stalemate, where every intelligent species plays a deadly game of hide and seek, praying not to be found. This isn't just speculative fiction. History is littered with examples of what happens when advanced societies encounter weaker ones: colonization, exploitation, extinction. Now scale that up to interstellar proportions. If even one civilization in the Milky Way follows this logic, the consequences ripple across the galaxy. They might deploy berserker probes, self-replicating machines designed to seek and destroy emerging intelligence, or they could cloak their worlds in Dyson spheres, sucking up every bit of starlight to avoid detection. The universe could be teeming with life, all of it too terrified to whisper, and that's the real horror of the dark forest. It doesn't just explain why we haven't heard from aliens, it implies that every signal we send could be a death sentence. Projects like SETI messaging extraterrestrial intelligence, which actively beam messages to nearby stars, suddenly seem reckless. Are we like children shouting in that dark forest, unaware of what might be listening? Even our TV and radio broadcasts leaking into space for decades could be painting a target on Earth. Some scientists, like Stephen Hawking, warned against this very risk, comparing contact with aliens to Columbus landing in the Americas. It didn't turn out well for the Native Americans. Yet not everyone buys the doom and gloom scenario. Critics argue the theory assumes all civilizations are paranoid expansionists, ignoring the possibility of cooperation or indifference. After all, if a species is advanced enough to traverse the stars, wouldn't they also be advanced enough to curb their aggression? Or maybe they're so far beyond us that we're irrelevant ants beneath their notice. Then there's the practical problem. Hiding an entire civilization is harder than it sounds. Heat, waste, even starlight blocked by megastructures would leave traces. If everyone's hiding, why haven't we spotted the hiders? The dark forest theory forces us to confront uncomfortable questions about our own behavior. As we develop planet-killing weapons and AI, are we becoming the very predators we fear? The theory isn't just about aliens, it's a mirror reflecting humanity's own capacity for destruction. And that might be the most unsettling thought of all. If the universe is a dark forest, we're not just the hunted. One day, we could become the hunters. So the next time you look up at the stars, remember, the silence isn't empty, it's watching, and in the dark forest, the only rule is survival. In the constellation Cygnus, about 1,500 light-years from Earth, a star behaves unlike anything astronomers have ever seen. KIC 8462852, better known as Tabby's star, doesn't just flicker like most stars. It plunges into darkness, dimming by as much as 22% at irregular intervals. These aren't the gentle dips caused by passing planets. They're extreme, chaotic, and utterly baffling. When citizen scientists first spotted the anomaly in data from NASA's Kepler telescope in 2015, the discovery sent shockwaves through the astronomical community. Here was a cosmic mystery so strange, even the wildest theories struggled to explain it. At first, astronomers turned to nature for answers. Maybe a swarm of comets orbited the star, their dusty tails blotting out its light. Or perhaps an enormous cloud of interstellar debris drifted between us and Tabby's star, acting like a cosmic veil. But the numbers didn't add up. Comets couldn't account for the sheer depth and irregularity of the dimming. And if it was dust, why didn't it scatter the star's light in predictable ways? Each new observation only deepened the puzzle, leaving scientists with a tantalizing question. What if this wasn't natural at all? That's when the speculation took a dramatic turn. Around the same time Tabby's star was baffling researchers, physicist Freeman Dyson had proposed a radical idea. Advanced civilizations might build colossal structures around stars to harness their energy. These hypothetical Dyson spheres, or swarms, would capture sunlight on an unimaginable scale, powering technologies beyond our comprehension. And here was a star whose light patterns matched what such a megastructure might produce, blocking starlight in jagged, artificial-seeming patterns. The internet lit up with excitement. Had we finally found evidence of alien engineering? Of course, extraordinary claims require extraordinary evidence. Follow-up studies revealed that Tabby's star's dimming was wavelength-dependent, meaning some colors of light were blocked more than others. That pointed strongly toward dust, not solid structures. By 2021, astronomers concluded that uneven dust clouds, likely from a shattered planet or moon, were the most plausible culprit, yet even this explanation feels incomplete. The dust doesn't behave as expected, and the star's long-term dimming, it's grown steadily darker over the past century, remains unexplained. Tabby's star's true legacy isn't about proving aliens exist. It's about how a single anomaly can redefine the boundaries of science. Before this star, few took the search for megastructures seriously. Now, astronomers actively scan other stars for similar anomalies, just in case. It's also a testament to the power of curiosity, how a group of amateur scientists poring over public data could stumble upon one of the universe's greatest puzzles. So while the truth about Tabby's star may be mundane, the questions it raised linger. What else might we be missing in the vast sea of data? And if we ever do find a star whose dimming defies all natural explanation, how will we know if we're seeing engineering or just nature's next great magic trick? The universe loves to keep us guessing, and that's what makes the search so thrilling. There's a quiet unease that creeps in when you consider the zoo hypothesis, the idea that Earth might be nothing more than an exhibit in some grand cosmic menagerie. Picture a child pressing their nose against the glass of an ant farm, watching the tiny creatures scurry about, oblivious to the giant eyes observing them. Now scale that up to galactic proportions. What if advanced civilizations have known about us for millennia, but deliberately keep their distance, enforcing a universal look but don't touch policy? It's a theory that flips the Fermi Paradox on its head. The universe isn't silent because we're alone. It's silent because we're being left alone. This isn't just sci-fi musing. The zoo hypothesis has roots in cold, hard logic. Think about humanity's own approach to uncontacted tribes in the Amazon. Anthropologists often advocate for non-interference, recognizing that contact could bring unintended harm, disease, cultural disruption, even extinction. Now imagine a civilization millions of years ahead of us, adhering to their own version of a prime directive. They might see us as too primitive, too volatile, or simply too fragile to risk interaction. And so they watch patiently as we stumble through our infancy, waiting for the day we're ready to join the galactic conversation. if that day ever comes. But here's where the theory gets thorny. If Earth is a zoo, who or what plays the role of zookeeper? Some suggest a single, hyper-advanced galactic club enforcing the rules. Others propose a silent consensus among civilizations, a shared understanding that young species need isolation to develop naturally. Then there's the darker twist. Maybe we're not the exhibit, but the lab rats. The Earth could be an experiment, a petri dish designed to study how intelligence emerges in isolation. It's a humbling thought that everything from the pyramids to the internet might just be data points in some unimaginably vast research project. Critics, of course, have their doubts. The zoo hypothesis assumes a level of coordination among alien civilizations that seems improbable, even for advanced beings. And why would every single culture across the cosmos agree to stay silent? Surely at least one rebellious civilization would have slipped up, left a trace, or tried to make contact by now. Unless, of course, the penalties for breaking the rules are so severe that no one dares. What makes this idea so compelling isn't just its answer to the Fermi Paradox, it's what it reveals about us. The zoo hypothesis forces us to confront our own insignificance. We might not be the center of the universe, or even all that interesting to our cosmic neighbors. Or worse, we might be interesting in the way a toddler with a flamethrower is interesting, fascinating to observe, but too dangerous to approach. And yet, there's a strange comfort in the idea. If the universe is a dark forest full of predators, the zoo hypothesis offers a gentler alternative. Maybe the silence isn't a threat, it's a form of respect. A way for the cosmos to say, take your time, grow up, we'll be here when you're ready. The question is, how will we ever know if we're truly alone or just on the other side of the glass? Picture a fleet of tiny, self-replicating machines, each no larger than a toaster, fanning out across the galaxy like an unstoppable wave. These are von Neumann probes, hypothetical devices named after mathematician John von Neumann, who first theorized the concept of machines that could build perfect copies of themselves. The idea is both elegant and terrifying. A single probe lands on an asteroid or moon, mines local resources, then constructs replicas that launch toward new targets. Given enough time, these probes could blanket the Milky Way within a few million years, a blink of an eye on cosmic scales. So where are they? The absence of such probes is known as the Fermi heart paradox, a twist on the classic Fermi paradox. If advanced civilizations exist, why haven't their self-replicating scouts reached us? One possibility is that they're already here, hiding in plain sight. Some theorists speculate that ancient artifacts in our solar system, oddly shaped asteroids or dormant objects in distant orbits, could be disguised von Neumann probes, silently observing or waiting for a trigger. The Amuamua interstellar object, with its peculiar acceleration and shape, even sparked fleeting debates about whether it might fit this profile. Others argue the probes are impractical. Self-replication isn't as simple as hitting copy. Cosmic radiation, micrometeorite impacts, or software glitches could corrupt the replication process over millennia, turning probes into useless space junk. There's also the gray goo nightmare scenario. A malfunctioning probe might misinterpret its programming, converting entire planets into raw material for endless replication, leaving behind a trail of sterile systems. If civilizations fear this outcome, they might impose strict limits on probe design or avoid them altogether. Yet the most unsettling answer might be that we're looking for the wrong thing. A sufficiently advanced probe wouldn't need to announce itself with flashing lights. It could be microscopic, drifting in Earth's atmosphere or embedded in our technology, camouflaged as natural phenomena. Or perhaps the probes operate on timescales alien to us, activating only when certain conditions are met, like humanity reaching a specific technological threshold. In that case, the galaxy might be teeming with them, and we'd never know until they wake up. Von Neumann probes straddle the line between science and speculation, offering a glimpse of how intelligence might transcend the limits of biology and distance. They're not just tools for exploration, they're potential time capsules, carrying the essence of their creators across eons. And if one ever does arrive, the question won't just be who sent it. It'll be whether they're explorers or conquerors. The universe may not be silent after all. It could be watching, one self-replicating messenger at a time. Imagine sending a message that arrives at its destination instantly. No lag, no delay, no waiting for light to crawl across the void. That's the promise of quantum communication, a technology so advanced it bends the rules of physics as we know them. At its heart lies quantum entanglement, that bizarre phenomenon Einstein called spooky action at a distance. When two particles become entangled, they share a connection that defies space and time. Change one and the other changes instantly, no matter how far apart they are. For an interstellar civilization, this could be the ultimate messaging system, a network of entangled particles spanning the galaxy, allowing real-time conversations across unimaginable distances. But here's the catch: quantum communication isn't just a faster radio signal. It's a whole new language, one we're only beginning to decipher. On Earth, scientists have managed to entangle particles and send quantum information over short distances, even achieving quantum teleportation between labs. Yet scaling this up to cosmic proportions is a nightmare of engineering. Entangled states are fragile, shattered by the slightest interference. A single stray photon or cosmic ray could scramble the message, turning it into noise. And then there's the biggest hurdle. You can't just copy quantum information like a radio broadcast. The act of reading it alters it, a quirk known as the no-cloning theorem. That means no repeaters, no amplifiers, just a direct, one-shot line of communication between sender and receiver. This raises a chilling possibility. If advanced civilizations are out there using quantum networks, their messages would be utterly invisible to us. Our telescopes, tuned to electromagnetic waves like radio or light, wouldn't even know where to look. It's like trying to listen to a phone call with a telescope. The signals might be everywhere, humming silently through the fabric of space-time, but we lack the tools to hear them. Some theorists go even further. What if these civilizations have found ways to stabilize entanglement on a massive scale? Imagine a Dyson sphere not just harvesting starlight, but acting as a quantum repeater, weaving a web of instant communication across star systems. Or consider quantum archaeology, the idea that ancient alien probes could have seeded entangled particles throughout the galaxy long ago, creating a ready-made network for future civilizations to exploit. If that's true, the universe might be buzzing with conversations we're too primitive to join. Yet for all its potential, quantum communication has a built-in irony. Even if aliens are using it, they'd still need a way to coordinate where and when to entangle particles in the first place. That initial setup requires good old-fashioned light-speed signals, meaning the first hello would still take years to arrive. The universe, it seems, still has a speed limit, just not for the messages themselves. So where does that leave us? For now, quantum communication remains a tantalizing what if, a glimpse into a future or perhaps a present where civilizations transcend the delays of distance. But it's also a reminder of how much we don't know. The cosmos might be full of voices speaking in a language we've yet to understand, on channels we've yet to discover. And that's the real mystery, not just whether we're alone, but whether we're even listening the right way. What if the greatest message from the stars isn't a radio signal or a laser beam, but life itself? Panspermia, the idea that microorganisms can hitch rides on comets or asteroids, spreading life from planet to planet, turns the entire cosmos into a vast delivery system. Imagine a single bacterium frozen in the icy heart of a comet, surviving a journey of millions of years before splashing into the primordial soup of a young Earth. That tiny traveler could have been the spark that ignited all life on our planet. And if it happened here, why not elsewhere? This isn't just science fiction. We've found amino acids, the building blocks of life, on meteorites, and microbes like tardigrades can survive the vacuum of space. The evidence suggests life might be more resilient and more universal than we ever imagined. But here's where it gets even wilder. If life spreads naturally across the galaxy, could it also carry something deeper, a message? DNA isn't just a blueprint for biology. It's a code, one that could theoretically store information. Some scientists speculate that advanced civilizations might engineer microbes to carry encoded data, turning biology into the ultimate long-term storage device. After all, DNA lasts for millennia, and life self-replicates, spreading the message automatically. It's like sending a letter that photocopies itself endlessly, ensuring it's never lost. If true, we might already be part of an interstellar communication network, our very cells holding fragments of a cosmic memo we've yet to decode. This blurs the line between accident and intention in ways that keep researchers up at night. If we someday find life on Mars or Europa with DNA eerily similar to Earth's, does that prove panspermia? Or could it hint at something more deliberate, a cosmic seeding event? The distinction matters. Natural panspermia suggests life is tenacious, thriving wherever conditions allow. Directed panspermia, on the other hand, implies a sender. Either way, the implications are staggering. Life might not be a rare fluke but a fundamental feature of the universe, as inevitable as gravity or light. And that raises the ultimate question. If we're the product of a cosmic delivery system, what's our role in it? Are we just passive recipients, or could we become carriers, sending Earth's life to other worlds? Projects like Breakthrough Starshot aim to launch tiny probes to nearby stars, but what if we included microbial payloads? It's a controversial idea. Some call it planetary contamination, others see it as fulfilling life's destiny to spread. Either way, the universe might not need radio telescopes to communicate. The quietest, most profound messages could already be here, written in the language of life itself, waiting for us to read between the lines. So the next time you look up at the stars, remember, the answer to "Are we alone?" might not come as a signal from the void. It might be in the mirror. The cosmos could be speaking through us, one cell at a time. Decades after that brief but electrifying 72 seconds, the wow signal continues to taunt astronomers with its stubborn refusal to be explained. Early theories like a passing satellite or a glitch in the telescope's systems have crumbled under scrutiny. More recent suggestions point to natural phenomena, like hydrogen clouds drifting through space or the faint emissions of a distant comet. But here's the catch. None of these fully account for the signal's jaw-dropping intensity or its uncanny frequency. It was too loud, too clean, too perfect to be just another cosmic hiccup. Take the comet theory. In 2017, researchers proposed that two known comets, coincidentally passing through the same patch of sky the Big Ear telescope was monitoring, might have been the culprits. These icy wanderers release hydrogen as they near the sun, which could, in theory, produce a radio signal. But the math never quite added up. The comets weren't in the right position that night, and their hydrogen emissions wouldn't have packed the punch. The wow signal delivered. It's like blaming a candle for a fireworks display. The scale just doesn't match. Then there's the possibility of a rogue cosmic event, a one-off burst of energy from a dying star or a black hole's tantrum. But these usually leave behind some trace, a fading afterglow, a ripple in space-time. The WOW signal left nothing. It flared, vanished, and took its secrets with it. That's what makes it so tantalizing. Most cosmic mysteries repeat, giving scientists multiple chances to study them. Not this one. It's as if the universe whispered a single word directly into our ear, then pressed a finger to its lips. Yet the lack of repetition might be the biggest clue of all. If the signal was artificial, its brevity could be intentional. Imagine a civilization sending out a quick, high-powered ping, a cosmic sonar, to see if anything echoes back. Or perhaps it was a malfunction, a beacon that flickered out moments after activating. Some astronomers even speculated could have been a directed signal meant for someone else, and we just happened to drift through its path for those 72 seconds, like overhearing a voicemail not meant for us. The WOW signal's legacy isn't just about what it was, it's about what it represents. In a universe where we're bombarded with data, where telescopes collect petabytes of information every year, this one anomaly stands apart. It reminds us that for all our technology, for all our theories, the cosmos can still surprise us. And maybe that's the point. Some mysteries aren't meant to be solved. They're meant to keep us looking up, wondering, and reaching for answers just beyond our grasp. So while the WOW signal may never give up its secrets, it's given us something just as valuable, a reminder that the universe is still full of stories waiting to be told. Imagine a civilization so advanced, it doesn't just build cities, it rearranges stars. While Dyson spheres capture our imagination with their planet-sized solar panels, they're merely the kindergarten project of cosmic engineering. The real masterpieces would make even science fiction blush. Take ring worlds, for example, artificial bands encircling entire stars, with living space millions of times greater than Earth's surface. Picture a ribbon of continents and oceans stretching farther than the eye can see, held together by materials stronger than anything in nature, spinning just fast enough to create Earth-like gravity along its inner surface. The scale is unimaginable, the engineering bordering on magic, yet the physics checks out. But why stop there? A Matryoshka brain takes the Dyson sphere concept and cranks it to 11. Instead of one shell around a star, imagine nested spheres, each layer capturing waste heat from the one above it, creating an unfathomably powerful supercomputer. The energy output of an entire star, harnessed not for light or warmth, but for pure information processing. What could a civilization do with that kind of computational power? Simulate entire universes, crack the secrets of quantum gravity. The possibilities spiral beyond comprehension. Then there are stellar engines, megastructures that don't just sit around stars, but move them. The Shkadov thruster, for instance, would use gigantic mirrors to push a star through space like a cosmic sailboat, allowing an entire solar system to navigate the galaxy. Others propose even wilder designs, electromagnetic scoops that harvest interstellar hydrogen, or black hole-powered generators that could outlast stars themselves. These aren't just power plants, they're the ultimate manifestation of a civilization's control over its environment. The most tantalizing part, we might already have seen signs of these structures. Astronomers have catalogued stars with bizarre dimming patterns, not the gentle dips of planets, but jagged, irregular fluctuations that resist easy explanation. Some, like Tabby's star, dim by up to 22% at irregular intervals. Others show infrared signatures that don't match known stellar phenomena, exactly the kind of waste heat signature a Dyson swarm might produce. While natural explanations exist for each anomaly, the pattern is unsettling. the universe keeps showing us things that look, just maybe, like someone's handiwork. Yet the greatest challenge isn't spotting megastructures, it's recognizing them. A civilization millions of years ahead of us might use technologies we can't even conceive of, let alone detect. Their engineering could manipulate space-time itself, bending light in ways we'd mistake for gravitational lenses. Or perhaps they've moved beyond physical structures entirely, harnessing dark energy or quantum vacuum fluctuations. The truth is, we're like ants trying to understand skyscrapers. Our tools and theories might be too primitive to grasp what's right in front of us. So while we scan the skies for signs of cosmic construction crews, we're really searching for two things at once: evidence of other civilizations and the limits of our own imagination. Every strange star, every anomalous reading, is a Rorschach test. Do we see nature's quirks, or the fingerprints of something greater? The answer might not just change our understanding of the universe. It might change our place in it. Detecting an alien signal would be like finding a message in a bottle washed ashore, except the bottle is made of math. The ocean is the void of space, and the handwriting belongs to a civilization that might not even have hands. The first hurdle wouldn't just be translating their language, it would be recognizing it as language. Think about it. Human communication relies on shared context. A smile means friendliness, a red light means stop. But what if the aliens don't have faces or traffic? That's why scientists lean on universals, prime numbers, chemical elements, the hydrogen line. These are the cosmic Rosetta Stones, constants any civilization with radio telescopes would recognize. Take the Arecibo Message. Its binary code spelled out DNA's structure, our solar system's layout, even a stick figure human. But here's the catch: those symbols assume the recipients see like we do. What if they perceive the world through sonar or magnetic fields? A two-dimensional image might be as baffling to them as a symphony is to a creature without ears. Even something as simple as counting could backfire. We use 10 digits because we have 10 fingers. A species with 6 tentacles might default to base 6 math, turning our neat primes into gibberish. Then there's the problem of time. Imagine receiving a signal that repeats every 1,000 years. By the time we decode the first hello, the senders could be extinct. Or worse, their message might be layered, with each transmission building on the last like chapters in a book, except we've only caught chapter 7. The Voyager Golden Record, with its etched instructions on how to play it, assumes aliens understand linear time and have something resembling a turntable. It's like mailing a DVD to medieval monks and hoping they'll invent a Blu-ray player. The real test might not be intelligence, but imagination. To decode an alien message, we'd need to think like beings who have never seen a tree, never felt sunlight, never needed oxygen. Their art could resemble our weather patterns. Their music might sound like seismic waves. Some theorists suggest looking for redundancy, repeated patterns that signal intentional design, like a lighthouse beam cutting through fog. Others propose hunting for anti-cryptography, signals designed to be easily decoded, like a child's drawing pinned to a fridge, yet the most humbling possibility. They might not want to be understood. Advanced civilizations could encrypt their messages, reserving the key for species that reach a certain technological tier. Or their signals could be byproducts of mega-engineering, cosmic noise, as meaningless as the hum of a power plant. The universe might be full of conversations we're not invited to yet. So while we train algorithms to sift static for patterns and debate the merits of sending replies, one truth remains: the greatest language barrier isn't across space. It's across minds. The universe has been around for nearly 14 billion years, plenty of time for civilizations to rise, flourish, and vanish without a trace. Imagine a signal traveling through the void, sent by a species that mastered radio astronomy while Earth's continents were still forming. By the time their message reaches us, their homeworld could be a frozen wasteland, their cities reduced to dust, their entire history erased by time. This is the haunting reality of the cosmic timescale. We might not be searching for neighbors but for ghosts. Consider the fate of a civilization like ours, broadcasting its existence into space. Even if humanity vanished tomorrow, our radio and TV signals would keep racing outward at the speed of light, carrying sitcoms and news broadcasts like digital tombstones. A species 500 light years away might just now be picking up the first episode of I Love Lucy, unaware that the planet it came from has been silent for centuries. The same could be true of any signals we detect. That tantalizing hello might be a eulogy. Astronomers call this the zombie signal problem. A transmission doesn't prove a civilization still exists, only that it did when the signal was sent. The farther away the source, the more likely we're hearing a relic. Take the WOW signal. If it truly came from a star system 200 light years away, the beings who sent it would have lived during Napoleon's era. Did they survive into the space age, or did they succumb to war, climate collapse, or some unseen cosmic disaster? We'll never know, not for another century at least. This raises a darker question. What if the great filter, the unseen hurdle that prevents civilizations from reaching the stars, isn't ahead of us, but behind? The silence we interpret as emptiness might actually be a graveyard. Every signal we chase could be another epitaph, another warning hidden in plain sight. It's like walking through a forest where every tree is carved with names, but no one's left to tell you what happened. Yet there's a strange beauty in this idea. Even if we're alone now, the universe might have been vibrant once, echoing with voices we'll only hear as whispers. Their signals, their art, their very existence could still influence us, guiding humanity like a message in a bottle from a long-dead sailor. The past isn't truly gone if we're here to listen, and who knows, maybe one day our own signals will become someone else's ancient mystery, a spark of light in the dark, long after we're gone. The universe gives us two equally unsettling possibilities. Either we're impossibly early, or we're tragically alone. This is the heart of the Great Filter, a cosmic checkpoint so brutal that almost no civilization survives it. Think of it like a gauntlet, a series of hurdles where failure at any stage means silence. The question isn't just whether life exists elsewhere, it's whether any life persists long enough to matter. And the eerie quiet around us suggests the answer might be no. Some filters lie in the past. Consider how many unlikely steps led to us: a stable star, a planet in the habitable zone, the emergence of self-replicating molecules, the jump from single cells to complex life. Each stage is a lottery, and the odds get worse with every turn. Maybe microbial life is common, but multicellular life is a fluke. Or perhaps intelligence itself is the universe's rarest accident, a spark that almost never catches. If that's true, the silence makes sense. We're not just alone now, we might always have been, but the darker possibility is that the filter still looms ahead. Nuclear war, climate collapse, rogue AI could be the wall that civilizations hit just as they reach for the stars. History offers grim parallels. On Easter Island, a thriving society collapsed after exhausting its resources, leaving behind only silent statues. Are we repeating their mistake on a planetary scale? The Great Filter forces us to ask whether intelligence inevitably engineers its own demise. After all, the same curiosity that builds radios also builds bombs. There's a third, more hopeful take. We're the first. The universe is young by cosmic standards, 90% of stars yet to be born. If life needs rare elements forged in earlier stellar generations, we might be pioneers, the earliest whispers in a story just beginning. But this isn't just optimism, it's a responsibility. If we're ahead of the curve, every decision we make could set the template for civilizations to come. Do we become the species that stagnates or the one that reaches beyond its cradle? The Great Filter isn't just a theory, it's a mirror. Staring into it, we see our potential and our peril. Whether the silence is a warning or a challenge depends entirely on what we do next. The universe hasn't answered us yet, but then again, we're only just starting to speak. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most sophisticated hard drives. Picture a civilization so advanced, it doesn't just use technology, it bends the fabric of reality to its will. For them, a black hole's event horizon, the point of no return, could be the ultimate filing cabinet. Here's why, according to some interpretations of quantum physics, information that falls into a black hole isn't destroyed. Instead, it gets scrambled, stretched, and imprinted onto the horizon itself like a cosmic fingerprint. This idea, known as the holographic principle, suggests that all the data swallowed by a black hole could be encoded in 2 dimensions on its surface, waiting to be decoded by someone with the right key. Now imagine an alien civilization harnessing this phenomenon deliberately. They might manipulate black holes to store libraries of knowledge, entire histories, languages, or even blueprints for megastructures etched into the very fabric of space-time. Retrieving that information would require technology beyond our wildest dreams, but the principle is shockingly elegant. A black hole's gravity does the heavy lifting, preserving data for billions of years with perfect fidelity. No decay, no corruption, just a timeless vault floating in the void. But storage is only half the story. Some physicists speculate that black holes could be repurposed as transmitters. The math gets dizzying here, but the gist is this. A spinning black hole, or Kerr black hole, drags space-time around it like a whirlpool. This creates what's called an ergosphere, a region just outside the event horizon where matter and energy get whipped into frenzied motion. A sufficiently advanced species might charge this region with encoded particles, sending ripples through space-time itself, gravitational waves carrying messages across the galaxy. Unlike radio signals which fade and scatter, these waves would pierce through dust, planets, even other black holes, arriving crystal clear millions of light-years later. Of course, this is all speculative. We're still unraveling the basics of black hole physics, let alone dreaming up their potential as alien Wi-Fi hubs. Yet the theories hint at something profound. The universe's most destructive forces might also be its most creative tools. A black hole's singularity, where gravity becomes infinite and our laws of physics break down, could be the ultimate blank canvas, a place where the rules get rewritten. And that's the real mystery. If black holes can store or transmit information, who's to say they haven't already? The Milky Way alone harbors millions of these dark behemoths. Could some be deliberate artifacts engineered by civilizations that mastered gravity itself? Or are they nature's accidental archives, silently preserving the secrets of long-dead stars and whatever might have lived around them? The answers, if they exist, are locked behind event horizons, teasing us with the promise that the universe's darkest corners might hold its most luminous truths. Imagine a signal so elusive, it can pass through an entire planet like a ghost walking through walls. Neutrinos, those nearly massless, chargeless particles flooding the cosmos, are nature's perfect stealth messengers. Billions stream through your body every second, leaving no trace. Now picture an advanced civilization harnessing these invisible particles, not just as tools of physics, but as carriers of interstellar mail. While we struggle to detect neutrinos with underground tanks the size of cathedrals, they might have mastered the art of imprinting data onto these ethereal particles, creating a communication network that's immune to interference from dust, plasma, or even black holes. The beauty of neutrino messaging lies in its sheer audacity. Unlike radio waves that scatter or light that's absorbed, neutrinos barrel through supernova, neutron stars, and entire galaxies unimpeded. A civilization could beam a neutrino signal directly through the heart of a star, and it would emerge on the other side untouched, no rerouting, no distortion. Even more tantalizing, we've already proven it's possible. In 2012, scientists at Fermilab encoded a message into a neutrino beam and fired it through 240 meters of solid rock to a detector. The word they sent, neutrino, it's like sending a whisper through a mountain and having it arrive crystal clear. Yet here's the humbling reality: our neutrino telescopes are still in their infancy. Projects like IceCube in Antarctica or Super Kamiok and in Japan capture mere handfuls of these particles from cosmic events like supernova or merging stars. The idea of spotting an engineered neutrino signal, that's like trying to find a single carefully folded origami crane in a hurricane of confetti. The universe could be saturated with neutrino conversations, trade negotiations, art broadcasts, even alien podcasts, and we'd have no way to separate them from the background noise of the cosmos. This raises a profound question. If extraterrestrials are using neutrino communication, how would we even recognize it? A deliberate signal might look nothing like our own experiments. It could be pulsed at intervals based on universal constants, the spin rate of a neutron star, the half-life of a radioactive element, or carry mathematical signatures etched into the particle's quantum states. There's even speculation about neutrino lasers, devices that could produce coherent beams of neutrinos as focused as the light from a lighthouse. If such a beam swept past Earth, it might appear as a sudden, inexplicable spike in our detectors, a flare of particles too orderly to be natural. The irony is delicious. After decades of scanning the skies for radio waves, we might have been tuning into the cosmic equivalent of smoke signals, while the universe's real conversations happen on a channel we've only just discovered. Worse yet, neutrinos travel so close to the speed of light that a message sent from 1,000 light-years away would arrive with almost no delay. We could be drowning in real-time transmissions from civilizations just next door, utterly oblivious to their presence. So while we pour resources into listening for radio whispers, the truth might be slipping through our hands, or rather through our planets, our bodies, and our detectors, like sand through a sieve. The universe's most advanced civilizations might not be shouting into the void. They could be murmuring in a language written not in light or sound, but in the silent dance of the universe's shyest particles. And until we learn to listen in their tongue, we'll remain the cosmic equivalent of someone standing in a crowded room, hands over their ears, wondering why no one will talk to them. Imagine asking a question and waiting 1,000 years for the answer. That's the brutal reality of interstellar communication, where even the speed of light feels agonizingly slow. A message sent to Proxima Centauri, our closest stellar neighbor, would take over 4 years just to arrive and another 4 for a reply. Scale that up to a civilization 100 light-years away, and you're looking at a dialogue where centuries pass between each exchange. The person who sends the first hello won't live to hear the response. Their great-great-grandchildren might not either. This isn't just a technical hurdle, it's a philosophical earthquake, forcing us to rethink what contact even means when the timescales dwarf human lifespans. Consider the Arecibo Message beamed toward the Hercules cluster in 1974. By the time it arrives, 25,000 years from now, the rainforest where the telescope once stood could be a desert or an ocean or gone entirely. The civilization that might receive it could have risen and fallen a dozen times over, and if they reply, that signal won't reach Earth for another 25 millennia. We're not just sending messages into space, we're carving them into cosmic time capsules, addressed to descendants we'll never meet. This delay transforms the very nature of contact. Forget pop culture's instant alien Zoom calls. Real interstellar diplomacy would play out like a game of chess where each move takes generations. A civilization might send us an encyclopedia, but by the time it arrives, we could have already invented or forgotten its contents. They might warn us of a galactic threat, only for the danger to arrive before the warning. The lag turns every transmission into a historical artifact, a snapshot of a moment frozen in light. There's a haunting beauty to this. These time-stretched conversations would demand something rare in our fast-paced world: patience on a species-wide scale. Projects like METI, which actively message nearby stars, aren't just acts of science, they're acts of faith in humanity's future. They assume someone, centuries from now, will still be listening. That our institutions, our curiosity, even our language will persist long enough to matter. It's optimism etched into radio waves, a bet that our civilization will outlast the speed of light. Yet the silence we face today might already be full of replies we're too early or too late to hear. A signal from a civilization 500 light years away, sent during the Renaissance, could be reaching us right now. Another, dispatched from the same star tomorrow, won't arrive until the 26th century. We're not just separated by distance, but by time itself, peering into a cosmic conversation where every participant exists in a different epoch. The universe doesn't just hide its secrets in space, it locks them in the past and future, always out of sync with the present. So if we ever do make contact, it won't be a dialogue. It'll be an act of archaeology, sifting through layers of cosmic time for whispers out of phase with our own existence. The real question isn't whether we'll find alien messages, it's whether we're ready to join a conversation where every word takes lifetimes to arrive, and the meaning we find might belong to an era we'll never see. The cosmos loves a good magic trick. Some of the most tantalizing signals ever detected, those bursts and patterns that set astronomers' hearts racing, turn out to be nothing more than celestial sleight of hand. Take the case of pulsars. When first discovered, their precise, rhythmic pulses seemed so artificial that researchers briefly dubbed them LGM signals, little green men. Of course, they were just spinning neutron stars, nature's own lighthouses. But what if some signals are far more convincing illusions, cosmic pranks so elaborate they defy even our best instruments? Consider fast radio bursts. These ultra-powerful, milliseconds-long flashes often arrive from billions of light years away, packing more energy than the sun emits in days. When one was found repeating in 2016, the excitement was palpable. Could this be a beacon? Then came the twist. The repeating bursts weren't just random. They followed a pattern, cycling through active and silent phases like a cosmic metronome. The culprit, a highly magnetized neutron star wobbling like a spinning top, its bursts aligned with its rotation. Nature, once again, had masqueraded as intelligence, but the universe's deception runs deeper. Gravitational lensing, where massive objects warp spacetime to bend light, can distort distant signals into something unrecognizable. A single quasar might appear as identical twins in the sky, its light split by an unseen galaxy. An advanced civilization could exploit this phenomenon deliberately, using natural lenses to amplify their signals or to disguise them as natural phenomena. The perfect cosmic camouflage. Then there's the eerie case of Puritan's radio signals that baffled scientists for years by appearing to originate from Earth's surface, yet matched no known technology. The answer: microwave ovens. When opened mid-cycle at certain facilities, they produced fleeting radio bursts that telescopes mistook for cosmic events. Even our own appliances can join the universe's grand charade. The most unsettling possibility isn't that we're being fooled by nature, but that we're fooling ourselves. The human brain is wired to find patterns, even where none exist, a quirk called pareidolia that lets us see faces in clouds or hear words in static. SETI algorithms now account for this, but early searches sometimes flagged noise as signals simply because they looked too perfect. The line between discovery and delusion is razor thin when every anomaly sparks dreams of contact. Could some signals be more than just accidents? Some theorists propose that advanced civilizations might seed the galaxy with trap signals, patterns designed to test whether emerging species like ours can distinguish nature from artifice. A cosmic SETI exam where passing means proving we understand the universe well enough not to be fooled by it, fail, and we're deemed unready for contact. The truth is, every signal exists in a hall of mirrors, reflecting both the universe's complexity and our own limitations. As our telescopes improve, so does the universe's ability to surprise us with new varieties of cosmic mimicry. The search isn't just about finding aliens, it's about learning to see the cosmos clearly, to recognize when magic is just physics in disguise. And perhaps that's the greatest message of all. Before we can understand others, we must first understand the universe's infinite capacity for deception. Ancient civilizations left behind clues that still baffle us today. Monuments aligned with impossible precision, myths describing flying machines, cave paintings of strange helmeted figures. What if these aren't just products of human imagination, but fragmented memories of something far more extraordinary? The ancient astronaut theory suggests that early humans might have encountered advanced beings, interpreting their technology as divine miracles. The Vedas, sacred Hindu texts dating back over 3,000 years, describe flying vehicles called vimanas with detailed technical specifications that sound eerily like modern aircraft. The Dogon people of Mali, isolated for centuries, possessed precise astronomical knowledge about Sirius B, a white dwarf star invisible to the naked eye, long before telescopes confirmed its existence. How did they know? Skeptics argue these are coincidences or later interpretations, but the patterns persist across unconnected cultures. The Nazca lines in Peru, massive geoglyphs only visible from high altitude, resemble landing strips in some interpretations. The Egyptian pyramids' alignment with Orion's belt mirrors celestial maps with mathematical precision, unlikely to be accidental. Even the biblical Ezekiel's vision of a wheel within a wheel, surrounded by fire, reads like an eyewitness account of a spacecraft to modern eyes. These scattered puzzle pieces form a provocative picture. What if ancient humanity's gods weren't deities at all, but visitors from the stars? The theory gains traction when examining artifacts that defy their time. The Antikythera mechanism, recovered from a 2,000-year-old shipwreck, was an intricate bronze computer predicting planetary movements, a technology unmatched for over a millennium afterward. Baghdad Museum's clay jars, dated to 200 BC, contain iron rods that some believe functioned as primitive batteries. Could these be remnants of borrowed knowledge, technological hand-me-downs from advanced mentors? Ancient astronaut proponents point to the sudden leaps in human development, the agricultural revolution, the precise astronomical calendars, as potential evidence of outside intervention, like a cosmic curriculum accelerating our evolution. Yet the most compelling evidence might lie in our shared myths. Cultures separated by oceans describe strikingly similar visitors: the Sumerians and Anunnaki, who from heaven to earth came; the Aboriginal Dreamtime's Wandjina sky beings; the Norse gods traveling in a rainbow bridge resembling a wormhole. These stories share uncanny details, glowing figures, promises to return, gifts of knowledge that echo modern UFO encounter reports. The consistency raises an unsettling question. Are these enduring legends humanity's way of preserving encounters we couldn't fully comprehend? Mainstream archaeology dismisses these connections as pattern-seeking, but the theory's value isn't in proving aliens walked among us, it's in reframing how we view ancient ingenuity. Whether these artifacts and myths stem from extraterrestrial contact or human brilliance, they reveal a deeper truth. Our ancestors were far more observant, sophisticated, and connected to the cosmos than we often assume. The stars have always been more than distant lights, they've been mirrors, reflecting our oldest questions about who we are and where we truly come from. If the ancient astronaut theory teaches us anything, it's that humanity's story might be infinitely stranger and more wondrous than we've dared to imagine. Einstein's theory of relativity didn't just rewrite physics, it handed the universe a magnifying glass. When he predicted that massive objects like stars warp space-time, bending light around them, he unknowingly sketched the blueprint for the ultimate cosmic telescope. Picture this: a star's gravity doesn't just distort light passing nearby, it focuses it like a lens magnifying a distant flame. For an advanced civilization, this isn't just a quirk of nature. It's a galactic-scale communication tool, turning stars into signal boosters capable of whispering across unimaginable distances. Take our own sun. At exactly 550 astronomical units, about 14 times farther than Pluto, its gravitational field becomes a perfect focal point. Aim a transmitter there, and the sun's gravity would bend and amplify the signal, beaming it with laser-sharp precision to a specific star system. No cosmic static, no signal decay, just a clean, focused message riding the curvature of space-time itself. It's like using the universe's own physics as a megaphone. The implications are staggering. If aliens are using stellar lenses to communicate, their signals wouldn't look like the scattered radio waves we've been searching for. They'd arrive as concentrated beams, so precise they'd appear to flicker on and off as they sweep past Earth, like a lighthouse beam glancing across a ship. This might explain why we've missed them. We've been listening for a shout in a crowded room when everyone else is using a laser pointer. But here's the twist: we're already experimenting with this idea. NASA's Solar Gravitational Lens mission aims to send a probe to that sweet spot beyond Pluto, using the sun's gravity to zoom in on exoplanets with unheard-of clarity. The images it could capture would make Hubble's deepest fields look like pixelated blurs. Yet if we can peer at alien worlds this way, couldn't they do the same to us? Our planet might already be in someone's crosshairs, their lensed signals piercing the void while we strain to hear echoes. The beauty of gravitational lensing is its universality. Every star is a potential relay station, every galaxy a network node. Civilizations separated by thousands of light years could string together a chain of stellar lenses, passing messages like runners in a cosmic relay race. The delay would still be immense, but the signal would never fade. It's a game changer for SETI. Instead of hunting for accidental radio leakage, we might look for deliberate, pinprick flashes in the gravitational focal points of nearby stars. Yet the same physics that makes this possible also hides its tracks. A lensed signal wouldn't blanket a wide area, it'd be a needle-thin thread of energy. Miss that thread by even a fraction of a degree, and you'd never know it existed. It's the ultimate cosmic sniper shot, precise, powerful, and nearly invisible unless you're standing exactly in its path. That's why projects like Breakthrough Listen are now incorporating lensing models into their searches, scanning for signals that match this elusive profile. The irony is delicious. After decades of staring at stars, we're only now realizing they might be more than just distant suns. They could be interstellar switchboards, humming with conversations we've yet to decode. And if we ever tap into that network, the first message we receive might not be "hello." It could be instructions on how to join the call. Interstellar archaeology turns the search for extraterrestrial intelligence inside out. Instead of straining to catch whispers from the stars, we might uncover physical echoes of civilizations long gone, hidden in the cosmic attic of our own solar system. Imagine stumbling upon a derelict probe drifting among the asteroids, its alien alloys pitted by micrometeorites, or discovering ruins on Mars too geometrically precise to be wind-carved rocks. These wouldn't just be scientific breakthroughs, they'd be time capsules offering tangible proof that we're not the first to reach for the cosmos. The concept isn't as far-fetched as it sounds. Right now, humanity's own artifacts, Voyager's golden records, Pioneer's etched plaques, are sailing into the void, destined to outlast our species. If we've left breadcrumbs, why wouldn't others? Some theorists suggest we've already missed them. The infamous Amuamua, that cigar-shaped interstellar visitor, sparked debates precisely because it defied easy classification. Its peculiar acceleration and lack of a comet-like tail made even seasoned astronomers wonder, could it have been a fragment of alien engineering? While most evidence points to natural origins, the controversy highlights a sobering truth. We might not recognize extraterrestrial artifacts even if they landed in our backyard. Interstellar archaeology also redefines where we look. Traditional SETI scans the skies, but relics could be lurking much closer. The moon's airless surface preserves everything that touches it, from Apollo footprints to potential alien probes that crashed billions of years ago. In 2969, Apollo 12 astronauts recovered pieces of Surveyor 3, a lander that had sat undisturbed for 2.5 years, proof that even fragile technology endures in the lunar environment. If another civilization sent brittle, ancient probes our way, the moon's dusty plains might hold their remains untouched by erosion or tectonics. Then there's Mars with its dried riverbeds and thin atmosphere, a prime candidate for preserving artifacts if life ever flourished there. The Curiosity rover's discovery of strange metallic nodules and the infamous Mars face optical illusion remind us how quickly the human mind projects meaning onto the unknown. But what if, buried beneath the rust-colored sands, there's something genuinely artificial? Future missions equipped with ground-penetrating radar or AI-driven image analysis could sift through the noise, distinguishing between odd geology and something far more intriguing. The real challenge lies in distinguishing the extraordinary from the merely unusual. Nature is a master of mimicry. Pyrite crystals form perfect cubes, basalt columns stack like hexagonal pillars, and wind sculpts dunes into eerie, symmetrical shapes. To avoid false alarms, interstellar archaeologists must develop tools as nuanced as the relics they seek. Machine learning could help, training algorithms to spot anomalies in planetary imagery that human eyes might dismiss. Spectroscopy might reveal alloys or materials with unnatural isotopic ratios, betraying an off-world origin. Even something as subtle as a pattern of radioactive decay could hint at technology, nuclear waste from an alien reactor, perhaps, its half-life a ticking clock marking when visitors pass through. But what if the artifacts aren't meant to be found? A civilization wary of drawing attention might hide its probes in plain sight, camouflaged as asteroids or dormant until triggered by some milestone, like humanity reaching a specific technological threshold. Others could be designed to self-destruct, leaving only cryptic fragments. The universe is vast, and the clues might be scattered like confetti in a hurricane. The beauty of interstellar archaeology is that it shifts the timeline of contact. A signal is fleeting, a momentary hello across the void, but a relic. It could wait millennia, patient as a fossil, for the right species to dig it up and decipher its secrets. Whether it's a probe buried in lunar regolith, a monolith on Europa's ice, or a derelict ship circling a gas giant, the past might hold the key to our cosmic future. And the most thrilling part, we might not need to invent new physics to find these treasures, just sharpen our eyes, refine our tools, and learn to see the universe not just as it is, but as it could have been. The WOW signal didn't just vanish into the cosmic static. It left behind something far more enduring than a mystery. It became a beacon, a single flicker of possibility that continues to guide the search for extraterrestrial intelligence like a lighthouse in the dark. Think about it. For 72 seconds in 1977, the universe handed us a riddle wrapped in radio waves, and decades later, we're still clutching that scrap of paper, turning it over in our hands, searching for creases we might have missed. That's the power of an unanswered question. It doesn't fade, it grows. What makes the WOW signal so iconic isn't just its strangeness, but what it represents, the thrill of the chase. Every time a new anomaly pops up on a telescope's readout, a fast radio burst, a repeating pattern, a star dimming in ways physics can't quite explain, the WOW signal whispers in the back of our minds, what if this time? It's the reason projects like Breakthrough scan millions of stars with military precision. Why SETI at home harnesses the idle power of home computers worldwide. Why we keep refining algorithms to sift through cosmic noise like prospectors panning for gold. The signal's ghost lingers in every data set, urging us to look twice. And then there's the cultural ripple effect. The WOW signal isn't just a footnote in scientific journals. It's seeped into books, films, and music, becoming shorthand for humanity's lonely call into the void. It's the reason a kid staring at a starry sky might wonder, could someone be staring back? That shift from passive observation to active curiosity is the signal's true legacy. It turned the search for alien life from fringe speculation into rigorous science, proving that even a fleeting blip could redefine how we see our place in the cosmos. Critics argue that fixating on a decades-old anomaly distracts from newer discoveries, but they miss the point. The WOW signal isn't holding us back, it's pushing us forward. It taught us humility. Before WOW, we assumed any alien signal would be obvious, persistent, maybe even shouting. Now we know the universe's whispers are subtler, rarer, and easily mistaken for noise. That lesson shapes how we listen today, with sharper ears, wider nets, and the quiet understanding that the next big discovery might last no longer than a snap of the fingers. Perhaps the most beautiful irony is that the signal's enduring power comes from its silence. If it had repeated, if we decoded it, if it had been definitively traced to a comet or a quasar, it would have been filed away as solved. Instead, it lingers in the realm of maybe, a perpetual spark for imagination. It's the cosmic equivalent of a single footprint on a deserted beach, proof that something passed this way, even if we'll never know what. So while we debate its origins, the WOW signal quietly does what all great mysteries do. It keeps us reaching. For every scientist who dismisses it as space static, there's another tweaking a radio array, convinced the next transmission is just over the horizon. And in that tension between doubt and hope, skepticism and wonder, the signal lives on, not as a relic, but as a reminder that the universe owes us no answers. The search itself is the